Get ready to blast off into mind-bending territory. If we could reach the speed of light, we'd be zooming around our planet 7 times in just 1 second or hurtling back from the moon in under 3. Even better, we'd explore the galaxy at lightning-fast hours instead of years. But buckle up because as you near that cosmic speed limit, things start getting trippy. Time dilation and space contraction will warp your spacecraft's reality, making it a journey like no other. And when you finally do hit light speed, hold onto your seat because it won't be pretty. Join us in this video to find out what happens when we push physics to the edge. Think you'd love zipping across space at incredible velocities? Well, think again. Reaching nearly the speed of light might have some major downsides. Let's say we're able to blast off to our Martian colonies in just 10 minutes. That's half the speed of light, hitting an astonishing 150,000 kilometers per second. According to no laws of physics, this should be possible, right? But hold on tight because things are about to get weird. Stay safe back there. Let's take a step away from our screens for now. You see, scientists at MIT have created an out-of-this-world video game that lets us experience what hitting the speed of light would be like without actually breaking any rules or laws of physics. But before we dive into this cosmic adventure, let me just clarify why a quirky village with giant mushrooms and hooded cultists. Who knows? The main goal is to explore the mind-bending effects of approaching the speed of light in a fun, interactive way that doesn't require us to blast off at breakneck velocities. Now let's talk about what happens when we hit that cosmic speed limit. Well, not really hit it, but get close. In this game, collecting orbs makes our virtual light slow down, kind of like Einstein's theory says it should. Every orb you grab boosts your speed by 3,000 km per second. A serious rush, right? And here comes the cool part. As soon as we reach just 20% of the speed of light, things start to look really different. Objects in front of us become almost weightless and take on this eerie purple hue. Now let's check out what happens when you glance back at home base while cruising at this mind-blowing speed. Get ready for a shock. You'll see our world turned into a desolate red landscape. This isn't some sci-fi movie trick. It's the Doppler effect in action, the same phenomenon that causes galaxies hurtling away from us to appear redder and dimmer, while those zooming towards us, like Andromeda, seem more purple. Buckle up because we're about to push the speed limit all the way to half the speed of light. At this crazy velocity, get ready for an intergalactic acid trip. The Doppler effect will give you infrared and ultraviolet vision, turning your journey into a psychedelic experience. And the best part, it's not just about looking cool. As you glance left or right, these spectrums will change in real time. Just remember, in our world outside this cosmic adventure, reaching such speeds would be fatal. But let's keep exploring. Scientists often call space a vacuum, yet it's far from empty. While we can't breathe there, outer space is actually teeming with unseen elements waiting to be discovered. Now, let's talk about what's actually in our cosmic neighborhood. It's not just empty space between Earth and the Moon. Did you know that every cubic meter is packed with up to 10 million atoms? That's right, it's not a vacuum, it's more like a molecular soup. And here's the thing, when you start blasting off towards Mars, these tiny particles will transform into high-speed projectiles, potentially threatening your spaceship. So, buckle up tight because at just 20% of the speed of light, the stunning purple shift isn't the only visual effect you'll experience. You might also witness some fiery explosions on your spacecraft's surface. Let's dive deeper into what happens when you're hurtling through space at incredible velocities. Each heavy atom, like oxygen, can cause a mini explosion on your spacecraft's surface, and we're talking about just one single atom. Meanwhile, the light hydrogen nuclei that are everywhere in space can slip right through the coating and unleash radioactive chaos inside your ship, making it way more hazardous than Chernobyl. By the time you reach half the speed of light, your trusty spaceship will be severely damaged, with a cabin full of passengers who've had to endure unimaginable radiation exposure. But here's some silver lining. In this high-stakes game of cosmic tag, even a tiny dust speck can become your worst enemy. At such breakneck speeds, colliding with that speck is like detonating a thermonuclear bomb right on board. Here's what scientists have figured out so far. Shielding your spaceship with protective screens might help fend off individual atoms, but when it comes to a dust particle, all bets are off. So, if you were thinking of zipping to Mars in record time, Sorry, that's not happening anytime soon. However, if you're feeling adventurous and want to make the jump from our solar system into interstellar space like Voyager 1 did, then maybe we can give it a shot. The good news is, out there, a cubic meter of space contains an incredibly low amount of atoms, just 1,000 to 100,000 in total. This tiny number might just work in our favor if we design our spacecraft super slim and slap on a cone-shaped shield to deflect those mini explosions from many atoms at once. Who knows? We might just be able to push past half the speed of light and make history, though this cosmic gamble comes with no guarantees. If we somehow manage to outrun the odds and make it past half light speed, but then encounter a rogue particle, well, let's just say our prayers won't be enough. However, that's not even the worst of it. As we keep pushing our spacecraft to go faster, all sorts of crazy stuff starts happening. So buckle up, because we're about to dive into what would happen if we tried reaching, or even exceeding light speed itself. A feat straight out of sci-fi. Let's return to our trusty game at MIT and collect some more science points, shall we? If we're zipping along at 80% the speed of light, get ready for a visual showstopper. The Doppler effect kicks in big time, creating an incredibly bright spot that makes it almost impossible to look ahead. It's like trying to drive into the blinding sun. The image is surreal. It's as though someone torched space with a cosmic cigar, and you'd rather keep your eyes on the road ahead. The view behind you, nothing but an all-engulfing darkness. This is because, at 80% light speed, light from your surroundings can't keep up. It's like trying to catch up to radio waves from your own past self. But here's where things get truly mind-bending. If we pause the Doppler effect and take a peek at what's happening, you'll see something that looks eerily familiar, like a sci-fi jump drive. As you zoom past distant objects, they seemingly drift further away into the distance. Your view stretches out like a canvas, with your destination on the horizon moving at incredible speed. But here's where things get wild-eyed. According to Einstein's relativity theory, this isn't how it should look from inside your speeding ship. He predicted that if you were cruising close to light speed, everything in front of you would appear squished and flattened, like a funhouse mirror reflection. Even our home planet Earth would be transformed, looking more like a flat disk than the round orb we know, an incredible visual effect that's out of this world. Flat Earthers, get ready for some mind-blowing science that'll make you rethink Einstein's views on your theory. Kind of. Here's what he got right when you're hurtling towards light speed. Everything in front seems squished and flattened, just like we discussed. But there's a crucial catch even Einstein didn't consider. As time appears to slow down for the traveler, something else happens that completely flips our previous idea. It takes longer for light from objects ahead to reach your eyes. This delayed information creates the illusion of a stretched-out view, and that's why everything seems farther away than you'd expect. Einstein's genius hid a surprising consequence of reaching near light speeds, and it has nothing to do with your view getting stretched. As you rev up your spacecraft engine, the energy fueling your journey doesn't just power motion, it transforms into mass. And we're not talking about just a little bit more weight here. According to Einstein's calculations, if you reach 90% of light speed, your spacecraft will basically weigh double what it did before. This drastic increase in mass creates a catch-22. You'll need even more energy to keep accelerating. But where's the extra power coming from? So, with this massive boost from extra energy turned mass, you'd think your spacecraft could finally catch up to light, right? Not quite. Einstein's theory slams on the brakes, saying it's physically impossible for anything with mass, and that includes spaceships and people, to reach or surpass the speed of light barrier. But here's where things get mind-blowing. News outlets often report scientists spotting objects breaking the cosmic speed limit. So, what's going on? Well, let me introduce you to this teeny tiny yet ancient speck on our cosmic horizon, one of the oldest known galaxies in the universe. Now, buckle up because this gets really interesting. This ancient galaxy is a whopping 13,400,000,000 years old. That's older than the universe itself was at its birth. However, when scientists measure how fast it's moving using something called redshift, they get a mind-boggling result: 32 billion light years away. That's right, this entire galaxy with millions of stars flew past us twice as fast as the speed of light. So why can't we do the same? Why does Einstein's rule still apply to us but not to this tiny speck on our cosmic map? But here's the thing, our universe isn't expanding like a perfectly inflated soap bubble. If it were, we'd only see galaxies within a certain boundary called the Hubble limit, kind of like being stuck in a small circle with no way out. However, when scientists point their telescopes towards the cosmos, they're surprised to discover that almost all the galaxies they can spot are actually 3 times farther away than what would be possible if we were just seeing a small sphere around us. That's right, from our perspective on Earth. Up to 97% of these galactic friends seem to have broken free from this cosmic speed limit. But here's where it gets really cool. The truth isn't that they've managed to move faster than light. Instead, the space between them is expanding at an incredible pace, taking them further and further away in a never-ending dance. Now, you might be thinking, but wait, isn't there a universal speed limit that even light can't break? And you're right, Einstein's laws do suggest just that. However, what if I told you there's something in the universe that doesn't play by those rules? Enter neutrinos, teeny tiny subatomic particles that are incredibly light, but not quite massless. In 2011, an experiment called OPERA at CERN's Large Hadron Collider created a stir when it detected neutrinos traveling at an astonishingly fast speed, nearly 307,000 kilometers per second. That's way faster than the speed of light, and the scientific community went wild. But here's where things get really interesting. This incredible discovery was later disputed due to some serious measurement errors, and it turned out that our understanding of physics still holds true. Nothing in our universe can move faster than the speed of light. The mystery remains, though. What else could be moving at incredible speeds just beyond our current grasp? But here's the plot twist. It turned out that those opera scientists were just a bit too hasty in their celebration. A loose cable connection was the culprit behind that supposed break of the speed limit, and the neutrinos weren't actually moving faster than light after all. But don't think for a second that this means Einstein's rules reign supreme across the universe. Far from it. Astronomers have been observing some seriously mind-blowing phenomena in distant galaxies. Take M87, for example, where a supermassive black hole is firing out plasma jets at a blistering 6 times the speed of light. Now, you might think this would throw Einstein's theories into chaos, but surprisingly, it actually supports his ideas. It just goes to show that sometimes, the universe has some truly cosmic ways of working around our so-called laws of physics. But hold up, those plasma jets aren't actually breaking the cosmic speed limit. They're just zooming along at a whopping 85% of the speed of light. So what's behind this illusion? It's all about perspective and time distortion, courtesy of Einstein's theory of relativity. Our line of sight and how time appears to slow down for objects moving close to light speed are 2 factors that make it seem like these jets are flying by at breakneck speeds. Now, if we were to attempt a crazy, non-existent space mission and somehow reach the speed of light, things would get weird, really weird. As we approach this cosmic speed limit, time would start to warp in extreme ways. And if we're lucky enough, or unlucky, to actually hit the speed of light, all we'd see is absolute darkness, an eternity of stillness that feels like forever. You could say our brave space traveler would be frozen in carbonite like stasis, suspended in a single moment for all eternity. Don't count out scientists just yet. They've been brainstorming some seriously clever ways to push past that speed of light barrier. Of course, there's a catch. These ideas come with mind-bending paradoxes that'll keep you up all night pondering the multiverse. But what if I told you there's already a totally legit way to zip from Earth to our cosmic neighbor, Alpha Centauri? In just 4 days, instead of the usual 4 years. Talk about a space travel game changer. It all comes down to a wild idea proposed by physicist Sergei Krasnikov back in the mid-90s. Picture this, a spaceship equipped with an energy drill that carves out a shortcut through warped space-time using tunnel passages, kind of like drilling through a wormhole. The result? A faster-than-light journey that's not only possible but has some serious real-world potential. Here's the scoop: this Krasnikov tube technology could have our regular spaceships blasting off to neighboring stars in just hours, not years or centuries. But what if I told you there was another genius who thought of a similar idea almost at the same time? It was 1994, and Mexican physicist Miguel Alcubierre was binge-watching his favorite show, Star Trek. He noticed how the Enterprise used its warp engine to warp space-time around it, allowing for faster-than-light travel. That's when Alcubierre had a brainwave. If far-off galaxies can move away from us at speeds above light, why couldn't we create our own warp engine? His design uses a special method to compress space in front of the spaceship and expand it behind, creating a warp bubble that lets it zoom through space-time. Who knows, maybe this Star Trek-inspired idea could be the key to unlocking the secrets of faster-than-light travel. Let's dive deeper into Alcubierre's warp engine concept. It works by creating a difference in pressure that forms a warp space bubble, basically, a protective shield around the spaceship. This bubble could potentially let our ship zoom past the cosmic speed limit, even reaching speeds a whopping 100 times faster than light. And here's the cool part. According to Alcubierre's design, the spaceship wouldn't actually gain that infamous relativistic mass, so it would stay in the same spot from its own perspective. So why haven't we built our very own warp-capable Enterprise yet? The catch, both Krasnikov tubes and warp engines require a special kind of fuel called negative energy. But here's the thing, we can't actually create that exotic stuff. Or can we? Enter German theorist Erich Lenz, who came up with a mind-bending solution to overcome this exotic fuel hurdle. He created his own version of a warp bubble, proving that maybe, just maybe, we're not as far away from building our own space-age warp engine as we think. Now let's address Erich Lenz's game-changing twist. He figured out how to power a warp bubble using regular energy, no exotic fuel needed. However, there's still a major issue. To make any substantial headway in reaching superluminal speeds, you'd need an insane amount of energy, equivalent to hundreds of Jupiter masses. That's not exactly feasible for your average spaceship, and it definitely doesn't fit the USS Enterprise's intergalactic travel style. But don't count us out just yet. NASA is dead serious about one day building a warp-capable ship, provided we can find ways to tame its energy appetite with new discoveries. Meanwhile, researchers at the University of Adelaide have been working tirelessly on an alternative approach, rewriting Einstein's equations to eliminate that pesky light speed limit altogether. Their early results look promising. So what will be the next hurdle once we break free from that cosmic speed cap? Get ready to have your mind blown as we venture into some truly trippy territory. Imagine your spaceship is cruising along at the speed of light, emerging from the vast darkness of space. And then you try to give it a little extra boost, adding an additional 60,000 kilometers per second. But here's where things get weird. When you hit light speed, time essentially stands still for you relative to the outside universe. Now, if you try to accelerate further, what happens is actually kind of counterintuitive. Your super fast acceleration starts moving backwards in time. Don't worry though, this isn't about traveling back into the past like in a sci-fi movie. Instead, it's more like your spaceship instantly shifts from warp speed to cruise control, slowing down dramatically as if it hit a massive speed bump. It's mind-bending stuff, but rest assured, our explorers won't be turning back time anytime soon. Hold on to your seat. We're diving deep into the wild world of physics. It's all about what happens when you try to push past the cosmic speed limit. Adding that minus sign to your calculations means you'll inevitably get thrown back in the other direction, like hitting an invisible wall at high speed. Every attempt to break free from light speed becomes a crash course in reality. And trust me, it doesn't end well. The math just isn't on our side when it comes to faster than light travel. As for your jelly comment, let's just say the thought of what happens aboard such a ship is more theoretical than delicious. Get ready for a photon power play. Here's the thing, photons aren't just light. They're tiny messengers that atoms rely on for crucial missions, absorbing and emitting energy when they switch gears in the atomic world. These photon delivery guys are super important. They help make chemical reactions happen and even bring electrons together to form unbreakable molecular bonds. And guess what? They work hard without any tips. But if you try to push past that magic light speed barrier, these busy little couriers will call it quits on their job, effectively shutting down the whole operation. So, if you tried to zip past that universal speed limit, the matter making up your trusty spaceship and even YOU would be too tangled up with itself to interact, effectively becoming useless. As for what happens next, buckle up, because things get wild. You could either turn into a tiny cloud of space dust or, in a cosmic explosion, unleash an energy equivalent to hundreds of atomic bombs, or maybe you do both at the same time. Either way, that pesky photon paradox would be the ultimate buzzkill for faster-than-light travel dreams. But here's a question: what if we could convince the universe to give us a more modest, yet super cool alternative? Faster-than-light travel might be out of reach, but how about instantaneous communication with friends on distant stars? That sounds like a cosmic win. And here's the thing: physics actually looks pretty promising for making it happen. Just last year, in September 2022, a team at Lawrence Livermore National Laboratory made headlines by claiming they'd broken the light speed barrier. And this time, it's not just clickbait. They genuinely achieved something groundbreaking that could pave the way for near-instant communication across vast cosmic distances. So, here's how they allegedly shattered the light speed limit: by harnessing intense lasers and plasma to boost photon waves to a mind-boggling speed of 390,000 kebers per second. That's 30% quicker than regular photons. You'd think this means we're on the cusp of superluminal Wi-Fi in our smartphones, but hold up. The catch: it wasn't actually the photons moving faster, it was more like the waves created by those photons that were given a speed boost. So, while this experiment is indeed revolutionary, don't expect your phone's internet to suddenly go intergalactic just yet. Think of it like this: when a pebble hits a pond, you get these ripples spreading out at an incredible pace. But the water molecules themselves aren't zooming across the surface, they're just gently swaying. That's kind of what's going on with these super speedy photon waves. They might be zipping along faster than light, but the actual photons themselves are still playing by the rules. So, this mind-bending trick can't transmit info. It's more like a cosmic party stunt that'll leave everyone surprised, not because of the message, but because of how fast it arrived. And let's not forget, even if we could harness this in space, there's no plasma pool to work with up there. Here's the thing: this faster-than-light trick needs a very specific setup: superheated plasma, to get those photons really moving. But there's another player in the quantum game that doesn't care about any of these rules, and it's called quantum entanglement. It's like an instant connection between particles, no matter the distance, allowing for some seriously fast communication. Think Mass Effect style. You know, that sci-fi tech where characters chat across galaxies in real time. Scientists are actually looking at this idea, and if we ever find a way to harness it, it could revolutionize how we communicate. Take Proxima b, our closest Earth-like neighbor. It's about 4 light-years away. If we had a way to tap into this entanglement magic, we'd be able to send messages to Proxima b in an instant. Imagine being part of a human settlement on Proxima b, our closest potential home beyond Earth. Getting there will take decades with current tech, but what if you could reach out to your friend on the ground in real time? That's basically what quantum entanglement allows: an instant connection between particles, no matter the distance. It sounds like science fiction, right? Picture this: you open a letter with part of the message from Earth, and instantly, another letter with the rest of the message opens for your friend on Proxima b. This defies Einstein's speed of light rulebook, so it's no wonder he was skeptical. But in 2022, scientists got the Nobel Prize for proving that quantum entanglement is real, giving us a glimpse into the mind-bending possibilities of this phenomenon. So, here's how quantum entanglement works. When you link two particles together, they become like cosmic twins. Change one particle, and instantly, the state of the other changes too, no matter where it is or what's between them. But for this instant messaging thing to work, we need a catch. We'd have to entangle those particles on Earth, send one to your friend on Proxima b, and then both you and your friend have to measure their state at the same exact moment. And here's the biggie: you've got to agree beforehand on what you want to say, because without that secret handshake or shared code, it's just random data. So while this does beat light speed messaging hands down, it's still a bit of a quantum catch-22. Think about it like this: opening a quantum entangled message doesn't give you the full picture. You need to know beforehand what's inside and how to interpret it. Plus, once you open that envelope, the magic bond between particles breaks, and there's no going back. Now, I know some sci-fi fans might be thinking of Mass Effect here. They solved this in their game by introducing special entangled particles that stay connected even after opening. But guess what? That just created another problem. How do you keep those fictional particles from being hacked or intercepted? Sorry, Commander Shepard, it looks like quantum entanglement isn't quite ready to save the galaxy. Yet, imagine Commander Shepard having a casual conversation with their buddies, totally unaware that one wrong move could mean game over for the entire universe. To grasp why faster-than-light communication is such a risk, let's dive into some genius math concepts thanks to Hermann Minkowski, Einstein's own teacher. Check out these diagrams. They'll help us visualize space and time in a super simplified way. See that horizontal line? That's space, buddy. The vertical one is time. Think of it as the timeline of our lives. Now look at that yellow diagonal line at exactly 45 degrees. This is the speed limit we all know, the light barrier. If your friend on Proxima b wants to reach you on Earth, they'll hop in a super fast spaceship but won't cross that yellow line. They'll stay safely below the speed of light. Now imagine your friend blasting off towards Proxima b on a super fast ride that won't break the cosmic speed limit. Meanwhile, you back on Earth have a top secret, super advanced FTL's faster-than-light transmitter, totally fictional, of course. So when you share your thoughts about that show finale with them, it looks like, from your perspective, a message zipping straight across the timeline, staying below Einstein's speed limit. But here's where things get tricky, and this is crucial to understanding why FTL comms are so dicey. Your friend, however, isn't as thrilled. They were planning on binge-watching that show during their interstellar journey. So, in response, they shoot back with a message of their own using the same FTL tech. Now picture the timeline. Your initial spoiler-filled message is like a horizontal line, but your friend's comeback. The plea to keep spoilers under wraps has to navigate both space and time. That's right, it has to cross that light barrier diagonally. And here's why this matters. According to Einstein's theories, if something can travel faster than light, it essentially moves through time as well as space. So, here's the kicker. Let's dive back into our interstellar drama. You've got your FTL transmitter spewing out messages, but what happens when it clashes with your friend's speedy request to keep spoilers hidden? To understand this cosmic conundrum, we need to take a step back and revisit that mind-bending concept of space-time warping. As your friend zooms towards Proxima b on their spaceship, they're essentially moving really, really fast. So much so that time starts to warp around them from the perspective of someone watching from Earth. Now, when your friend sends their message using FTL comms, it's like they're skipping across a distorted timeline. This isn't just a wild idea, it's actually how Einstein's theory of relativity works. According to this theory, as an object approaches the speed of light, time appears to slow down for that object relative to a stationary observer. So when your friend sends their message, what you see from Earth is not just a straight line across the timeline, but an angled one, because time has effectively slowed down for them due to their incredible speed. This isn't about making mistakes, it's all about how the universe works. Let's dive into this mind-blowing scenario. Think of it like a cosmic soap opera. So, when your friend sends their message from the spaceship zooming towards Proxima b, what you see on Earth is their message reaching us before we even send our own reply. But here's where things get trippy. If we look at this situation through the lens of physics and Minkowski diagrams, it's as if their message actually cuts straight into our past. They're effectively telling you to keep those spoilers under wraps before you've even had a chance to spill them on your show. It sounds like science fiction, but stay with me. There's more. If you don't send that reply, then how will you receive the response from your friend? But wait, you've already read their message. This is where things get really weird, and some scientists even think it could be so problematic for space-time itself that it might just collapse under the pressure of this paradox. So, buckle up. We're about to explore one wild ride through the world of relativity and time travel. Hold on to your seat as we tackle one of the most fascinating yet mind-bending concepts out there. The speed of light isn't actually about light itself. It's more like the universe's ultimate speed limit for how stuff can connect and interact. Now, this number might seem small compared to our everyday scale, but trust me, once you try to break free from this cosmic cap, things get really crazy. Imagine trying to push past this boundary. Suddenly, vibrant colors become blindingly intense, you'd gain an infinite amount of mass, and time would freeze solid. To put it another way, the quantum bonds that keep everything together just snap under the pressure. It's like the universe is saying, whoa, slow down. You're going to disrupt the whole fabric if you try to go faster than this. So there you have it. The speed of light isn't just a number, it's a fundamental rule that keeps our reality intact. Get ready for a thought experiment that'll blow your mind. Think of space-time as this delicate, intricate dance, and paradoxes are the cosmic equivalent of a reckless dancer crashing into everything in sight. The universe goes to incredible lengths to stop these destructive moves from happening, right? But what if we could do it all without getting tangled up in those pesky paradoxes? In theory, by sending super general messages that don't carry any specific details, like chatting about the weather or poking fun at Einstein's theories. We could essentially send info across stars instantly. It sounds like science fiction, but just think of it: no causality issues, no universe-destroying problems. It's like having a cosmic safe mode for communication. Imagine taking a super fast trip through